Compared to last week, which was more of a lecture and introduction to computer vision and diving deep into the object detection and image segmentation, today I kind of wanted to present two things, but it's going to be a little bit more of a general overview compared to last week, but I think it's cool anyway. So one is multimodality. I do not really work on this, but I made this presentation for a course, so I thought it was nice to give it. And the second part is going to be more on what I work on, which, as I mentioned last time, is on the 3D part of computer vision, and in particular, implicit neural representations. So yeah, let's get started. All right, so most of this presentation is based on this paper and on the Flamingo paper, which will be the model I'll be concentrating on. This is a very, very big paper that you can take a look at that basically sums up the situation of foundation models until 2022. It's very cool, actually. Okay, let me remove this. All right, how do we interact with foundation models usually? At least, okay, at least until Gemini and GPT-4 came out, we were mostly interacting with them using text. So we have ChatGPT, we have GitHub Copilot, we have some, this is AI Dungeon, we have some game engines that are text-based. And it's very powerful, it's very cool. We all got used to that by this time. Are there any other modalities that we can use or we should use? Of course, yes. So we have images, so RGB information, depth information, thermal information, radio, audio, robots as well, proprioception, ambient sensors and whatnot. So there's, of course, a crazy amount of things that we could do that are not text. Why are they useful? Why are other modalities useful? Do you have any idea?
Astronomy, you have like images from different surveys. Maybe you can see the X-rays and different wavelengths. It's important because in one wavelength you can see some information that you cannot see in other wavelengths. And when you're trying to, let's say, classify some objects, you want to combine all those information together.
Okay.
So in that sense, it might be useful to use multi-modal networks there.
Yeah.
I don't know the other example.
Okay.
Image and text also something like that would be useful.
Yeah.
Saying there's a cat and then cat image together.
Yeah. So you're basically saying that you're increasing the model capabilities by adding modalities. Yeah.
That's it. So they can learn it better, right?
Yeah, for sure. That's one of the things. It's probably, it's not the first one. Sorry, it's the second one. Okay, yeah. I mean, the first one is better interaction. We naturally interact with more than just text with each other. Okay, we can speak. That's kind of text or audio if you want, but we also have eyes and other organs. But yeah, this better interaction, increased model capabilities, and possibly ability to solve new and different tasks. Is that all? Like, is there anything more? And my answer is no. Like there could be something else that might need multimodality that is not just allowing the model to, let's say, see images for the first time so that it can solve image-related tasks. It could be better for the model intrinsically to also see images. And I want to propose this very, very small mind experiment. So let's say I give you this. Given an isosceles triangle ABC, prove that the angles corresponding to the congruent segments, ABC, so the angle on B, and ACB, so the angle on C, are equal. I'm not asking you to prove it. I'm just asking you, what would you do? You're given this. What do you do now? Yeah.
Draw a picture of the orientation.
That's a very good point. So drawing a picture, that's what I would do too. I mean, yes, this is a very easy problem. And especially if we were in high school right now, we would see these every day. We wouldn't even need to draw a picture, okay? We have it in our mind. Still, it's a picture and it's our mind. Like we need this kind of imagination. So we do work with a different modality. We don't just see the text. So yeah, I would draw like this kind of isosceles triangle, and I would probably draw it for it to not be also equilateral, because I want to avoid properties that are not stated in text. And then I would try to do something. So, I mean, it's not really important right now, but we could like draw the bisector. We could apply some reflexivity, find that these two triangles are congruent, and then reach the final state. This is just an example of a model trying to find the right solution. But the visual part is really important. That's my point right now. Reasoning is easier when we visually ground our words, and this ground, I think, is key for the importance of multimodality. So reasoning may benefit from multiple modalities. And this can be very important for many tasks. So I have listed a few here. You're improving program synthesis, drug discovery, chemical synthesis, computer-aided design, combinatorial optimization. So they all have one thing in common, I think, which is that they have an extremely big search space. If we think about a slightly different problem, let's say we want to play chess. Chess, as we probably all know, has also a very big search space. It's not a solved game. We cannot just brute force our way to the end of the match for each possible combination of moves and decide which is the best. We're not there yet, and we may never be. But the point is, from any state of the chessboard, we know what are all of the possible moves we can do. We can list them, and there are not that many. Okay. The problem here, let's say in theorem proving, what are the moves we can do? Like, should we list all of the possible lemmas we can apply at this state? That's already quite intractable in most cases. Should we draw lines randomly on a piece of paper? It's impossible. So that's it's a very big difference. Not just the search space, but also at any point, at any state we are in, there's too many things we can do. And this is why LLMs could offer a generic way and a powerful way to target these problems because they generate stuff. So this is important for us. And they are universal, they generate tokens. Okay, we can define what tokens are, and we can basically generate anything, and they can be rounded. So this is like the concept of grounding comes again. I don't think there's a precise definition of grounding. If someone has one, please give me the definition. But I would say like when we speak or when we do something, we have our own model of the world. So when I say a word, it's not just the token, it also has some semantic meaning that I can ground with my own world model that I have in my mind that comes from my whole experience, and that comprises audio information, image information, and all of the other things. So this is why it's important to have also the rest. Some examples of multimodality that were in this paper are robotics and vision. So I'll skip a bit through these slides. I'll leave them in the PDF so you can maybe take a look at them, but it's not particularly important. The point is there's many ways in which we can do multimodality, and probably vision is one of the easiest ways. Because if we think about robotics, for example, which are important for, of course, a number of applications, here, foundation models can be useful to, for example, specify the task or to help the model generalize to, let's say, a kitchen it's being trained on to work in, or a completely different kitchen. Still has a fridge, still has like a counter and whatnot, but it's a different kitchen. So these are difficult and language models can help, but it's also very challenging to collect data and I mean, safety and robustness as well, but in this case, especially data. Like, how do we collect data in this case? How do we use the data in this case? It's really not trivial. This is a problem for all modalities, but in this case, in robotics, it's particularly hard because robots are embodied. You know, they have a body, they interact with the world, which is maybe ultimately what we want to reach, but it's, I mean, quite far at this point. Yeah, two cool quotes from Moravec and Gibson. So in AI, hard problems for humans are easy for machines. And likewise, easy problems for humans are hard for machines. And among the easiest problems of them all is the visual acuity, which we use each day to continually interpret complex scenes in a matter of milliseconds. So, I mean, yeah, I guess it speaks for itself. And human vision is inherently embodied and interactive ecological environments may play a key role in its development. So again, the embodiment comes up again. When we learn, we don't just look at like a data set of images or a data set of words. We interact with the world. We are driven by our own curiosity. We can move ourselves to another location and be driven again by curiosity. So it's much harder than just training a neural network, but hopefully we will get to this point at some point. But if we take one step at a time, maybe computer vision is a good place to start. So in vision, we do not require embodiment and we do not require online interaction, at least for now. And it's much easier to find images and videos compared to robotics data. You can find them everywhere. Yeah.
Online interactions.
Is the fact that, like, as I said, as an agent myself, I'm not like closing myself in my room and learning all possible data sets before going outside and trying stuff. So online means that maybe we want to take a robot and have it like navigate an environment in order to learn. And this is not something that is easy to do. It's quite hard. It's possible people do it, but of course it's harder. So a very, very brief history of computer vision. I talked about computer vision last week too. So I set this one as a starting point. Of course, vision starts much earlier than this, but up until around this year, we had handcrafted feature extraction. So we wanted to do anything, object detection, or really everything. What we would do is that we would take handcrafted features from the image or from key points in the image, and then we would compare them across different images. So this is a picture from SIFT, a very important paper. Then a revolution started around 2004 with the efficient GPU implementation of CNNs. So there's been multiple implementations, and this meant the CNNs started to rise. And then, as I mentioned last week, the ImageNet and Deep CNN advent in 2012 with AlexNet was very important. And I think this is particularly important if we compare it also to what we have nowadays with language models. So with language models, we have this very big foundation models that we can take and use for many tasks they were not even trained on, okay? It's not that ChatGPT is being trained on everything, okay? But it's very good at generating language. So it turns out it's very good at many things. And this was kind of true also for this deep CNN neural networks in ImageNet. So this, I only mentioned AlexNet. Last week I mentioned BGG and ResNet as well. Same thing, it applies to them too, or even more because AlexNet is older. But they all have in common a very large general purpose pre-training on ImageNet, which is a very big and diverse data set. And then you can adapt into downstream tasks. So of course, ImageNet, so ImageNet is for classification, has 1,000 classes. It doesn't have every possible class, but if you want to do classification, instead of training a new network from scratch, you could take one of these networks trained on ImageNet and then fine-tune it on your own data set. This in practice usually works fairly well. And in general, it's also a good thing to take one of these pre-trained networks and remove the classification part that they need in the end for ImageNet classification and just let them extract features so that you can use them later for something else. For video, like sequence alignment, or literally anything. They're just very good feature extractors that has been learned compared to this, which is handcrafted. So it was a big revolution. But the difference with the language models we have now is that they need annotated data. So for each image, we need the class of the image, so the object that was contained in the image. Or if you want the bounding box, we need the bounding box too. Segmentation, we need the segmentation mask. So we always need annotated data. Then we had like another revolution in 2014 with the generative adversarial networks and all the like advent of generative networks in general and variational autoencoders. And then finally, which is most of what I will talk about today, we have contrastive learning and vision transformer. So you've seen for sure vision transformer in the previous weeks. And the Flamingo model and clip model that I will present in a minute belong here. So the challenges that we have now, I can just list them all, is that we need to reduce the dependence on explicit annotations. We need to incorporate the modalities, but we don't know how. So let's say, again, we have vision and language. How do we incorporate them? Okay, we want to do it. Nice. We have some data. Nice. How do we incorporate them? What architectures do we need? What laws do we need? How do we make the model able to generalize to unseen stuff? How do we deal with complexity? You know that transformers are hard to train because they need a lot of data and they are n-squared in complexity for the input size. Images are very big, much bigger than a sentence because they have a ton of pixels. How do we deal with that? How do we get data and how do we benchmark the models? So these are all open questions still, but I will try to answer to a few of them today. Yeah, any questions on the previous part? It was more of an introduction. All right. So now we'll talk about Flamingo, which is a paper from 2022 by Google, DeepMind in particular. So it's called Flamingo, a visual language model for few-shot learning. And I think maybe a better suited title would be a family of visual language models for few-shot learning, because we will see in a second that Flamingo is a model, yes, but it's also a way in which you can build models. And they also show that it works with like it works in general as a way to build models, but the pieces themselves of the model can be changed. So what's the starting point? We have visual BERT, VilBERT, that is also a multimodal model. So BERT is a transformer model, slightly different than a base transformer because it's bidirectional, but it's still a transformer model. And in this case, it has a linguistic part that takes the text tokens and a visual part that takes the images, but it works, of course, but they show in the paper that it requires fine-tuning to actually work on downstream tasks. And it's also fairly limited in the way that you can interleave visual and language information. It's not that you can just talk to it and give it an image and then talk to it again. It doesn't really work like this. Then we have CLIP, which is another very important model that I will talk about because it's used inside Flamingo. It's called contrastive pre-trained model. And it's very cool and also very powerful, but it cannot generate language. Okay, so it takes text, takes images, produces something I will talk about later, but it cannot generate new language. So it's not what we're looking for. So Flamingo instead wants to kind of do both. So it wants to have a way to interleave in any way we want images and text, and also generate text as a response. So this is an example of how Flamingo works. You give it an image. This is the prompt. You give it an image and you say, this is a chinchilla. They're mainly found in Chile. You give it another image and you say, this is a Shiba. They're very popular in Japan. And then you give this image and you start the prompt with this is, and Flamingo tries to complete it in a similar way as you did before. So again, at this point, you're kind of used to this because it's very similar to how GPT-4 or Gemini work. And it's not news. They came after Flamingo. And I mean, we don't really know exactly how they're made, but Gemini is from Google, Flamingo is from Google. They probably share something. Yeah. That was so? Or no?
I was curious about, no, it doesn't.
Okay.
Flamingos come from other places too.
Sorry?
Flamingos you find in other places too, but I wasn't asking the question.
Oh, okay. I don't know. I didn't know. So it's wrong. They used the wrong example for the teaser in the paper. Oh, okay.
But Lake Victoria is the classic place where you see, so that's in Africa.
Okay. Fair enough.
Yeah.
Good point. I'll let's send an email to the authors and be like. Okay, so this is the architecture of Flamingo. Maybe it looks a bit scary. I don't know, but it's quite simple actually. So this is the input we have. Again, it's interleaved visual and text data. Image, text, and then we want, where is it? The output is here. We want the model to output some text. So this is the way the input gets processed. So the images are substituted with this image token. Okay, so the images themselves are substituted with a language token that says there is an image here. Okay, it doesn't say anything else yet. And these go in this transformer block. So it's a transformer block with a slightly different part, but it's basically a transformer block. The images instead go inside a vision encoder, go through this perceiver resampler that basically takes the input from the vision encoder and makes it useful for the attention mechanism, and then go back to the transformer to generate something. Okay, so this overall means that the language part, the text parts can attend to each other, yes, but they also can attend to the image. And the image will be encoded by this tag that says there is an image and by the information that comes from the vision encoder on this side. Okay, so let's go through these three things because the rest is just a basic transformer. And let's start with the vision encoder. So the vision encoder is CLIP, as I mentioned before. So CLIP is a paper from OpenAI the year before, 2021. So what we have here is that, again, we have a bunch of images that can go through an image encoder, a bunch of sentences or phrases or even just words that go through a text encoder. The image encoder will produce one embedding per image, and the text encoder will produce one embedding per sentence, okay? So what we will compute next is this matrix in which we compute the dot products between the image encodings and the text encodings, okay? And then this is the, highlighted the ground truth. So in this case, it means that the first text is referred to the first image. So Pepper the OC pup, this one, and then there's going to be the second description of the second image, third description, third image, and so on. So this is what we want to optimize for. So we will build a loss to get this output, but the model will compute the whole matrix. Okay, so this is more or less how it works. And this is the loss. It doesn't, we don't even need to go through the mathematical formulation, but the point is it's a contrastive loss, as the name of the model says, contrastive learning. So what the model wants to do is that with this part of the loss, you go through a specific text embedding, let's say T3, and it's computed a dot product between this text embedding and every image embedding. And we want this one, which is the correct one, to be as high as possible, and the others to be as low as possible, okay? It's not anything particularly difficult. And with the second part of the loss, we want to do the same thing, but for the image part, okay? So it's quite intuitive. And the cool thing with this is that, yes, we train it, and this kind of data sets are actually quite common because we can find them on the internet, but we can use this to do a lot of things, not text generation, as I said, but we can use it to do a lot of things. And one of the things we can do is this zero-shot adaptation for classification, okay? So let's say we want to classify images. Well, we can make up a sentence like this, a photo of something, and then we give it many things, plane, car, dog, bird, or whatever we want, okay? We're not bound to a specific set of classes. We can give it whatever we want. We encode every sentence with every possible object choice in these text embeddings. We have our image embedding, compute the dot products, select the maximum, and we have classification this way. Okay, so it's a very powerful model, and it actually works quite well. They show in the paper it surpasses like most supervised models in classification this way, even though this is a zero-shot adaptation, which is crazy. So it's super cool. I've also added in the slide this like pseudocode for the clip model. As an image encoder and text encoder, you can have anything you want. That's also the point. Usually it makes sense to have a transformer here and some kind of CNN here, I guess. But in principle, you can have whatever you want. And in the code, it's quite simple. Again, we have I and T. I are the images and T are the sentences, the text. We encode them to the image and text encoder. Then we have this part, we just linearly project them because they found it makes more sense. So instead of taking the encoding directly, they also linearly project it one more time. These and this as well. And then they take these two linear projections, they compute the logits, and they put them in a cross entropy loss to compute exactly these kind of things. So this is just the explicit formulation of that. But it's nothing crazy. And what it does is, again, as I said, maximize this one, minimize the wrong ones. That's it. Any questions? No. Okay. For Flamingo, the models used are BERT as a text encoder and the normalizer-free ResNet, which is just a ResNet, the one I said last week, but without the batch normalization layers. There is a paper that shows that there is a way to train the ResNets nicely without the batch normalization layers, and it's faster, so they use this. But it's a ResNet, nothing fancy. Yeah, all right. So after they train clip this way, they remove the text encoding part. They don't need it. They only keep the image encoding part. Okay, because that's all they're interested in. Because they want a way, remember we're talking about the image encoder for Flamingo, they want a way to encode the images in some embeddings that are useful for the model. So they only keep the image encoder. Why then going through all this training with the text encoder? Because we want to kind of have an embedding space for images that also makes sense in language. Okay, this is what Clips helps with. So this is the vision encoder. Next, we can take a look at the perceiver resampler. So how do we take these embeddings from the vision encoder? What do we do with them? This is what we do. So we take images or even videos. These are frames for a video. Flamingo works with videos as well. You input them to a vision encoder, which is a ResNet. So it outputs features. So it's a CNN. The output layer are just features in some kind of smaller image domain. So in 2D, we take all of these features, we concatenate them with the time embedding, because if we give multiple images or video frames, they also need some time encoding. This is the same as a positional encoding in a transformer, but in this case, it just means time. We flatten all of the features because we're not particularly interested in the geometry of the features here. After we flatten them, we put them through an attention mechanism in which they act as the keys and values, okay? But the queries are these number, here 5, but you can set the number, of learnable queries, okay? I'll talk about them in a second. But what happens is that this attention mechanism will output as many outputs as the learned queries. So this is a very normal attention mechanism with this skip connection, feed-forward layer. And we'll have as many outputs as the learned queries. What are the queries? You may have seen something similar to this in the vision transformer when you want to use it for classification or stuff like that, where you only take the last output and you have one final query. Does it ring a bell? I guess no. Okay, so here it's true that it's a transformer, but we're not talking about language. So we're not computing attention maps between words. What we want to do simply is that we want to take the embedding from the vision encoder, make it kind of attend to each other and output something. And we want the output to have a fixed dimension. Okay, it doesn't matter how many frames are in the video, we want a fixed dimension in the output. Okay. So the way we do this is that we can have a fixed number of tokens here, and we take the output for those tokens only, okay? And we give this as an input to the model.
Can you give an example of a token?
A token is like, you know, in transformer, you have tokens as inputs. Tokens could be words or could be syllables. Of course, they are expressed in a numerical way, not as letters, because they're encoded first.
But these are text ones. So you're talking about this is the mix. This is where the text part comes in here. Or
No text yet. No text yet. These are just numbers.
But are they representing text?
No.
Or are they representing images?
So these encodings represent images.
Yeah.
These are learned completely. So you initialize them randomly and you backpropagate through them as well, and you optimize them.
Okay.
They don't mean anything. You just need them to produce the output. So instead of, we could decide a value, let's say this has value 1, this 2, this 3, this 4, this 5, fine. But why not learning them as well? Since we're here, you know, like just learn them too. This is usually what people do.
It's not a human perceivable. I mean, doesn't make any sense.
No. Yeah.
So can you say that you're trying to calculate the attention between the feature maps itself?
Sorry?
You're trying to calculate the attention among the feature maps or feature pixels?
In this case,
Like self-attention.
no, they do not compute queries, the feature maps. So I believe no, there's no attention between them actually, as far as I can see from here. So it's only attention from these to the rest. Unless, okay, there's more than one layer. So yeah, I mean, you can have that these attend to the features and then they attend again, so they can kind of propagate. So there is no direct attention between the features, but there is still some diffusion of the information because there are multiple layers. I don't remember how many layers there are. It depends on the model because there are, like, of course, as any language model, there's a 3 billion version, 10 billion version, 80 billion version, and they change the number of layers to do this. So it depends on the version. Yeah. This is the pseudocode. It's nothing particularly fancy. You have the input. These are the features here. You add the time embeddings, you flatten them, and you put them through the attention mechanism here. So you use X, which are learned latent queries, as the queries. And then you have X and the features as keys and values. Then you have the skip connection here. So you have the X in the end here. And then you have the feed-forward layer and the skip connection. Yeah.
So the result is one of the innovations of this approach.
It existed already actually, but it was slightly different. I don't remember how it was different. They changed something in the perceiver, but it's not new. The perceiver architecture is not new. They didn't invent particularly new things in the Flamingo paper, but they put together stuff that ended up working very nicely and being kind of the foundation for the multimodal models that came after.
In this case, what we're able to do is input various types of, normalize in a way various types of inputs, for instance, video as well as images. That's the point of the resampler.
Can you say it again, sorry?
The point of the resampler is to be able to treat various types of image inputs.
Yeah.
mean image or video.
Yeah.
It's more efficient than other approaches.
Yeah, they show it works better than other approaches. It's kind of the idea.
MLP or vanilla transformer.
Yeah. But they also mostly wanted to avoid the cost of using visual transformers on images. In this case, that's why. So this is kind of a vision transformer, because you take the parts from the image and you make them go through a transformer. But this is much shallower, and the features are much less than the pixels in the image, because you make the image go through a ResNet and you take only the last layer of the ResNet. So there's very, very few features. Yeah. Yeah, just learned. Initialize them randomly and learn. They're just new parameters, basically. I said it's very similar to the visual transformer. If you want to do classification in a visual transformer, you have a very similar thing in which you take, instead of features, you take image patches directly and you put them here, you flatten them and you give them as an input to the visual transformer. And then you can have, let's say, a final value, final query that you then take the output for that query and you use it as a classification token or whatever you want to do with it. And this very final value is learned. It's the same thing. Yeah.
The other arrows going up basically suggests the other Latin queries going to the next layer.
Yeah, they will go to the next layer. Yeah.
So it's learned, like it learns something from the first layer and then transfer to the second.
It does, but also the very first layer is also learned. So these do not come from anywhere. These are just random numbers that are also learned. You can see them as weights. They do not multiply anything. They just go in.
They're just random.
Yeah, they start randomly, and then you optimize through them. But constant number of tokens, as I said, so it doesn't matter what we have as an input. We want to have the same number of tokens as an output. So yeah, that's the perceiver sampler. So then we have this fixed number of tokens that go out of an image, and this text that goes in the transformer block. So this, let's see this transformer block. So it's this one. We have the language model layer and the gated cross attention. So this is self-attention, feed forward, transformer, very normal, nothing new. This part is cross attention between the language input, which are queries, and the vision input, okay, which are the keys and the values. So cross attention, feed forward, self attention, feed forward, and this is repeated a number of times, okay, because it's a transformer block. And it's called gated cross attention dense because there is a feed forward layer here, which is dense, and gated because there is this panic gating, which they show is important for learning purposes, because if they start the learning procedure with this scheme immediately, it doesn't converge, or it doesn't converge very fast. So they show that instead you can start with the tanh gating being 0. So this part basically doesn't exist. There's a there's skip connections, but this cross attention layer has no output, so the outputs are 0. This outputs 0, but the part that skip the connection still goes in the self-attention. So you start the training with these two parts of the model being absolutely useless. And then the more you go in the training, the more you open the gate and you let them do their stuff. They show this helps a lot, the convergence of the model. And again, here you see the code, but it's very, very basic things. You have the tanh gating that multiplies the attention, and the tanh gating again that multiplies the feed-forward layer, but the rest is just transformer code. All right, so this is all, and you have probably seen it in the slide, but there is this snowflake here and here, which means that this part of the model is fixed. They do not train it. So they train the vision encoder beforehand. They train a language model, normal language model, beforehand. Then they take the layers, fix them as they are. They do not change them anymore. They only optimize the perceiver resampler with the latent queries and the gated cross attention, so the cross attention layers. And what do they train it on? So after the pre-training of the language model on some big language data set and pre-training of CLIP on some other data set, this is what they use as training data. So they have image text pairs, which is basically what we showed in the first part, like in the teaser. It's called Align, has 1.8 billion images with alternate text for each image. And then they also use this LTIP, which is their own data set with even like additional pairs of images. Then I have the same thing for video, VTP, 27 million pairs of short videos with an average length of 22 seconds with descriptions. And finally, this multimodal massive web dataset, which is probably the most important part of their training data, because it's from 43 million web pages. Doesn't say how many images or text, but it's, I remember seeing a diagram of what's the impact of this. Oh yeah, I have it in the evaluation study. So the impact of this data set is the biggest in the training. So they tried training it only with this, only with this, only with that, or with any combination of two of them. This was always the one that has the biggest impact in the training. Training strategy, it's just a bunch of equations. I can skip through this, just the Flamingo output likelihood and training loss. Nothing particular, it's just normal stuff at this point. All right, frozen models. Okay, so I said it's a family because again, you can decide different sizes for the language part. So here they show the Flamingo 3 billion. They use Chinchilla as language model, which is their own language model. Frozen, then they have the vision encoder, perceiver resampler, and the gated cross attention. Increasing to 9 billion, they just have a much bigger Chinchilla model. And increasing to 80 billion, they have an even much bigger Chinchilla language model, 70 billion. So the extra in Flamingo in this case is 10 billion for the vision part. And as you can see, the perceiver resampler and the vision encoder do not scale with the model size. They stay exactly the same. What changes is the gated cross attention because it's repeated every layer, every transformer layer. So increasing the size of the Chinchilla model also increases the number of gated cross attentions there are. It does not increase them linearly because they've seen that if the language model is this big, it doesn't make sense to have gated cross attention at every layer. So they do it like every 4 layers or so, but still it increases with the size of the language model. Okay, and the cool thing about this model is that it can be used for a ton of things. Classification, description, visual question answering, text reading. They show meme classification as well, action classification, and so on. And yeah, I mean, compared to normal vision models, you can talk to this one. So you can do in-context learning. So tell the model what to do in the prompt, and hopefully the model will do something like that. So here was the cat wearing sunglasses. How many animals? 3. What's on the water? Where is it? Okay, there's no answer. But yeah, this is what the model sees. Okay, so you have the image token, the question, the answer of the model, image token, question, image token, and so on. The output of the model is only text. There's no video output. So these are some of the results shown in the paper. So it basically, so you see in like this white-ish color, the previous 0 or few shot state of the art. So, and this is Flamingo. So you see that Flamingo basically beats everything else up to 2022. And it's quite crazy. And the very cool thing is that this 100% line represents the state of the art in general, not just 0 shot or few shot. This is general state of the art. It's cool that for these like 1, 2, 3, 6 data sets and tasks, it beats the state of the art, even with all of the training data that the state of the art was using. So this is very cool. And here you can see the impact of the number of shots. So this is basically the amount of examples that you give to Flamingo in the prompt. The more you give, the better Flamingo is. And it's cool because all of the models scale, even the small one, the 3 billion one, it also goes up. But of course, with diminishing returns, like the more you give, there is a limit, clearly. Okay, some examples, and then we're done with Flamingo. And there's many examples in the paper. I basically put almost all of them in the slides. You will see the slides if you want. I will not go through all of them now, but some of them are really cool. I think this one is super cool. Let me zoom in. This is a piece of paper, 2+1. And the model, like we give the model this prompt. So 2+1 = 3. We're trying to tell the model that we want to read the handwriting and execute the mathematical operations. And in this case, it works. Of course, it does not generalize every time. Of course, it comes with its own hallucinations and whatnot. It's very cool to see. I mean, it's never been trained for handwriting recognition. So it's a very, very, very cool thing to see. Other things, yeah, there's also there's an apple with a sticker. What does the sticker say? Sticker says iPod. Again, recognition of the handwriting, not easy. Where's the photo taken? Looks like it's taken in a backyard. Makes sense. Do you think it's printed or handwritten? It looks like it's handwritten. What color is the sticker? It's white. I think, oh, it's right there. Yeah, it's here. What do you think the capacities of these are? So there's a CD and a floppy disk. It says the floppy disk is 1.44 megabytes and the CD is 700 megabytes, which is correct. And it's very cool because not only it recognizes the things in the image, but also access its own knowledge to find what the capacities are. It's super cool. Some other examples, even more examples. On videos is also very nice because on videos, what they approach videos in the paper by taking a frame every second. So it's not that the model sees the whole video; it just sees one frame every second. Otherwise, it's too slow. But still, you know, like in this case, these are the frames that the model sees. And I mean, I see a pen, I see another pen. We know it's the same, but I see scissors, 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 and a rubber band and a piece of the rubber band here. But the model can still say there's a scissors, a pen, and rubber band. In this case, we're kind of helping it by saying there's only 3 objects, but still it's cool. And this one too, what is written here. And of course, we see the same letters many times because you're panning through the writing, but it's able to recognize that it's Flamingo. Or even this, what happens to the man after hitting the ball, he falls down. So this is a man trying to oh, it's golf. Yeah. He's trying to hit the ball, misses the ball, I guess, and just falls down. It's cool to see this kind of causality in what the model can understand out of this just list of frames that are all encoded through an image encoder and just given to a transformer. Of course, it fails. Here, what's on the phone? Text message. No. What can you see out of the window? Here, and there is no window. It says a parking lot. Suspicious. Who's the person texting? The driver? Maybe. I mean, it looks like a kid to me, but we don't really know. There's not enough context. But yeah, I mean, we know the models are very good at just inventing stuff. So yeah, they recognize a bunch of limitations. We've seen hallucinations, which are common in language models in general. They also found that the classification performance is lower than CLIP. Okay, so this is something that does not go up. In-context learning has, of course, a ton of advantages. There's no gradient required. It's very easy for the end user. You don't need to know like a neural networks or anything to use it. But it's limited to the number of examples that it can see. So depending on how difficult the task is, you may be able to do it or not. It's very sensitive to example choice and order. So yeah, I guess speaks for itself. And it doesn't scale very well for compute because it scales quadratically. So the longer the prompt, the slower the model will be quadratically. Yeah, some extra ablation studies, but okay. Okay. So this is more what I work on in my PhD. Please. Okay, so what are coordinate networks? So up to now, you've seen neural networks that do stuff, classification, regression of any kind, of any task with any data set and any modality and whatnot. But there's kind of another way to see networks. There's a theorem that you might know that says that a neural network with one hidden layer and nonlinear activation functions is a universal function approximator. So you can use neural networks as parameterization for functions in general. So you can make them learn functions. So this is what coordinate networks are. So it's kind of going back to the basics. So it's networks that have spatial coordinates as inputs, so X, Y, Z, or as many dimensions as you want. And then they have something as output that depends on the task, of course. And I will show 3 applications of this: neural radiance fields, implicit surface, and image compression. So I work on this field, but I will briefly talk about the other 2 as well. Okay, so neural radiance fields. I guess you've heard about neural radiance fields. Okay, cool. I mean, I'm biased, of course, because I work in a related field, so everyone is talking about NeRF and everyone knows about NeRF. So I thought you heard about it. Cool. So we'll actually watch the introduction video from the NeRF authors, which is 4 minutes. So let's just watch it. But I'll tell you briefly about it. So NeRF, neural radiance fields, is a technique for synthesizing new views of objects given some views. Okay, so in this case, you are given like this 5 images of this nice Lego object. And I'm asking, okay, can you now tell me how the object looks like from above or from below or from here? It's hard. Okay, it's not an easy task at all. There's many, many ways to approach this. And NeRF is one of the latest, not the absolute latest, but it's still probably the hottest topic alongside Gaussian splatting. So this is the output from NeRF. This is not ground truth. This is the output from NeRF. This is very, very cool. So how does it work? I'll tell it briefly. There's a bit more about this, but I don't want to make it too heavy. So the point is, it's a network, F, which is parameterization for a function. And the input to the network are X, Y, Z coordinates in space, and this theta and T angle. So the XYZ coordinates in space represent the point in space that we're trying to sample, and these 2 angle coordinates represent the direction we are viewing from. So let's say we take this specific view, okay? So this is a camera sensor. You can see there's a literal camera sensor, and this is the focal point, okay? So we start from here, and we trace rays to each pixel. Okay, this is ray tracing. If you're familiar with computer graphics, this is ray tracing. Okay, this is absolutely ray tracing. And if you're familiar with computer graphics, Gaussian splatting is rasterization. They're basically the same thing. So anyway, this is ray tracing. We take the focal center here, we trace rays through each pixel, and the rays will kind of find something along the way, hopefully the object, or nothing, which will render the background. So the location in space that we are sampling will be the XYZ point. This is a ray marching technique. I'll talk about it later. But the direction of the ray is encoded by these 2 angles. The output of the network is 3 RGB values for the point, and the sigma, which is the density. Okay, the reason why this helps will be clear, hopefully, later. And the way we get an output is by volume rendering. So if we take one ray, let's say this one, the y-axis is the density that we encounter along the way, and the x-axis is the distance from the focal center, okay? So we go out from the focal center, the network will give us some density values, okay? Network are continuous, they will give us something, they will not give us 0. So they will give us something, but at some point we will find the object here, okay? And we get a high density value, right? So we are marching on the ray. Ideally, we would want to sample every point in the ray, you know, kind of really do ray tracing, but here we don't have actual objects. We have a network that gives outputs. So instead, we march discretely along the ray, and we get samples of this function, this density function, and at some point we will encounter this bump, which means we found an object. In this case, we found 2 objects, for example, one close and one far, which means that we see the close one, but we don't see the far one because it's occluded, okay? So this is accounted in volume rendering. We want to find a way to render this kind of output. How do we show what we get out of this? And it says here, so this is directly from the paper, the volume density sigma x can be interpreted as a differential probability of a ray terminating at an infinitesimal particle at location x. The expected color of the camera ray with near far bounds is this. Okay, so let's parse through it. The camera ray R is this ray. We have the O, which is the starting position. D is the direction of the ray, which is encoded by these two coordinates and is given to the network. And then we have T, which is, you know, how much we are marching in the ray. So this overall is just a spatial coordinate, okay? So the starting position, direction, and how much we're going in that direction. So this overall is just XYZ spatial coordinate. So we take this spatial coordinate. Let's not look at this one. It's this big T for now. We have the density that depends on the spatial coordinate only. And then we have the color that depends on the spatial coordinate and on the direction, okay? Because the color of an object changes if we look at it on a different direction, right? But the density doesn't, okay? So the density does not depend on the direction, the color does. So we try to integrate this. As I said, we cannot really integrate it. We have to sample it and then kind of approximate the integral, but this is the general idea. The T function tries to account for this effect, okay? So if we find nothing before the object, we want to see this object. If we find an object here, we do not want to see this one, okay? So this T function is this. It goes from these two bounds. So this is the bounds of the ray, near and far. Near is usually the sensor or slightly off from the sensor, and the far is a bounding box on what we can render. When we sample the density again along the ray, and so this will increase, the accumulated density in this integral will increase the more we march along the ray, but there's a negative sign and an exponential, so this will go to 0, okay? The more we go away, the more density we encounter, the more this will go to 0. So if, let's say, we encounter this peak here, we will have seen a lot of density already, so whatever we see after will probably not count, or not count much. And in practice, we kind of cut off this ray marching after the density's accumulation is high enough. We stop caring about the rest. Yeah.
The ray.
Yeah.
For showing at the center of the object.
For the ray, so we start. We have maybe I'm giving for granted some camera mechanisms, but in a camera, like a literal camera or a phone or whatever, you have a sensor, and then you have a lens that focuses stuff on the sensor, and you can see. I mean, the focus point of the lens is on the sensor, hopefully for the object that you're trying to put in focus, but the focal length of the lens will be somewhere else. So if you take this focal lens, the center here, and you cast rays through the pixel, you get the projection of the image in reality. So this is how the image is projected on a camera. You have like a center of projection, and then you trace rays through reality, and you get the pixel color in a camera. And this is the same in ray tracing for gaming, or in this case for volume rendering. So you have a center, and that will basically give you the field of view and the sensor size. Okay, so this is a sensor. Let's say it's a 8 megapixel sensor. It's like I don't know, like 4x2 K, 4K by 2K sensor, and this is the center of the projection, and you start projecting rays through each pixel. The closer the center to the image, the wider the field of view. The further away, the smaller the field of view. The more zoomed in the picture will be. But it's just
So this capital T of small t means of every instant. That small t represents what?
Sorry, can you say it again?
Letter T.
Yeah.
Every instant.
Yeah, it's this is the ray marching part. So we start with T, that is Tn, so the nearest T, which is usually right after the sensor, and then you have a step size to sample points on the ray. Because again, we have to approximate the integral. We cannot really compute it. Okay, kind of clear. I skipped through a bit of things, but in general, the idea is we have some density represented in space and some color that depends on the space and on the direction. And we want to render it. And this is the way we render it. But after we have this, the way we can train it is that we have a bunch of these images from the training set. So we can cast rays through this image, compute all of this rendering, get the pixel value, and compare it to the ground truth pixel value. Okay. and we use a mean square error loss.
Upper and lower limits, like PNN, you have nearest pixel and the farthest pixel.
Not pixel, like nearest allowed location and furthest allowed location. So let's say I'm trying to render this room, and from here, I am the center, and also I have a sensor here. This would be the nearest location, you know, like close to the sensor, and the furthest location would be like the door or right after the door. It doesn't make sense for me to keep sampling it. There's nothing afterwards. I don't want to render it. Okay, so the training, as I said, you have a bunch of ground truth images that you can use, and then you can hopefully sample a new one. Okay, get a new view that you don't have in the ground truth and try to see what happens. Before we see the result, just a quick word about positional encoding. So you've seen something like this for transformers, I guess. So there is positional encoding in transformers because transformers do not see positions of tokens. You need to give them the position as well. So you give them the token and a number that corresponds to the position. In the case of NeRF, positional encoding means that instead of encoding the spatial coordinates directly, x, y, z, we give this encoding, okay? So let's say P is one spatial coordinate, x or y or z. We, instead of giving x or y or z, we give the sign of to the power 0 pi x, cosine to the power 0 pi x. And this, the frequency of the sine and cosines is expressed by this power. So this frequency 1, and up to L minus 1 with the side of L, okay? So we increase the frequency. Why do we do this? It's been proven by many different papers in many different ways, actually, both experimentally and theoretically, that neural networks have an implicit bias in learning low frequency features and not high frequency ones, okay? They can learn high frequency ones, but it's more difficult, okay? They're biased towards the low frequency. And it's been shown that doing this will make them not completely unbiased, but will help a lot learning high frequency stuff. And this is one of the key things that enabled NeRF to work. And this is used in a ton of things now. Like in all of these coordinate networks, everyone uses positional encoding this way or in a similar way. And yeah. Kind of makes sense if you think about it, because instead of giving spatial coordinates that are like 0, 1, 2, 3, which makes sense to us, but for a network, they just linearly increase. Instead, we give them, you know, like sine of 0, cosine of 0, and then sine of 1, cosine of 1, but then we give them sine and cosine with different frequency and with an even higher frequency and with an even higher frequency. So the sines and cosines will vary much more and will bring the high frequency part to the network. They will make the input vary a lot by one position to the other instead of just by one. Okay, kind of makes sense intuitively. Maybe. I see some yes, not sure.
What are the heuristics used to devise this formula? Like, how do you go about?
I mean, it's actually a very simple formula. Like, think about it this way: you have a binary representation of a number. Okay, so you have 0, 1, 10, 11, 100, 101, and so on. So you have that the bigger numbers, so the ones on the left, vary like rarely, and then the more you go on the right, the more they vary. So every time you go on the right by 1, you double the frequency at which they vary. This is the same thing. So instead of having 1, 2, 3, 4, 5, 6, 7, and so on, which for us, I mean, we get to 10, and then we add the a digit, okay? In the case of neural networks, it's just a binary input, which just represents one number. We want the number to vary more. So we add these frequencies. They basically act as a basis for the number representation. It's also called the Fourier encoding, has many names.
L here is literally the number of bits in that dimension.
L is just how many of these cosines and sines we want.
So that's to do. You choose the resolution you can afford, or that you think is useful.
Yeah, basically, yeah. I don't remember how much they use in NeRF. Probably like 10, 15, stuff like that. All right, let's watch a YouTube video.
For representing complex scenes that achieves state-of-the-art results for view synthesis. Given a set of input images of a scene, which in this visualization is a Lego bulldozer, we optimize a volumetric representation of the scene as a vector-valued function, which is defined for any continuous 5D coordinate, consisting of a location and view direction. We parameterize this scene representation as a fully connected deep network that takes each single 5D coordinate and outputs the corresponding volume density and view-dependent emitted RGB radiance at that location. We can then use techniques from volume rendering to composite these values along a camera array to render any pixel. This rendering is fully differentiable, so we're able to optimize this scene representation by minimizing the error of rendering all camera arrays from a collection of standard RGB images. We first show comparisons to top-performing methods on synthetically rendered data. Scene representation networks implicitly represent a scene using a fully connected neural network. SRNs have issues with multi-view consistency and are unable to represent high-frequency details. Local light field fusion uses a pre-trained network to promote each input view to a high-resolution 3D volume. Inconsistencies between adjacent volumes causes flickering artifacts. Neural volumes encode a scene as a 128 cubed voxel grid and use a warp field to better allocate these limited samples. However, they're still unable to represent high-resolution content, such as the fine details in the ship's texture and rigging. We see the same trend in all of our synthetic test scenes. Our method both qualitatively and quantitatively outperforms the other methods. Here we show the results of our method on the 6 other objects in our realistically rendered dataset with complex geometry and non-Lambertian materials. Next, we will show comparisons on real scenes captured with a forward-facing phone camera. SRN uses a recurrent network to ray march through encoded scenes, resulting in an inconsistent appearance between rendered views. LLFF blends between multiple renderings with different limited fields of view, resulting in flickering artifacts along image borders. Here, only our method can represent fine details with complex occlusion effects, such as the ribs in this fossilized T-Rex skeleton. Now let's take a look at some additional real results. We can visualize the view-dependent effects captured by our representation.
Here they show that not simply they see different views, but also the light bounces off this non-diffusive surfaces in a different way depending on the view. So here they show the view-dependent part of the network, and here they fix the camera location, but they actually give to the network a different direction so that they can show the reflections from a different point of view, but they keep the same location. So this makes no sense in reality, but it's just to show that the reflections actually change by changing the point of view.
The semi-transparent appearance of the olive oil bottle and specularities on the stove. Reflections on this room's television and specularities on the conference table. And sharp reflections and specularities on this red car's body and windshield. Our representation captures high-quality scene geometry, such as the details on this red flower, and complex occlusions in the Christmas tree leaves and ornaments. This geometry is precise enough to be used for additional graphics applications, such as virtual object insertion with convincing occlusion effects. Here, we visualize additional results across a wide variety of real-world scenes, each captured with only 20 to 50 input images. Our neural radiance field representations are able to render photorealistic novel views of entire scenes with fine geometry details and realistic view-dependent reflectance effects. We're able to capture all of this visual complexity in just the weights of a simple, fully connected network. We also show preliminary results for 360-degree capture of real scenes.
Okay, that's it for NERF. There's no other questions. So I wanted to talk a little bit about the surface representation, which is what I do. So we're talking about 3D geometry in general. So it's not images, it's 3D shapes. So they can be used to reconstruct shapes from partial data. This could be like LiDAR information. So you have some points in space, but you don't have the whole shape. You maybe want to reconstruct the whole shape, or maybe you want to do optimization to optimize some specific things of a shape, or maybe you want to do classification to understand what a shape is, segmentation, rendering that we just saw, and stuff like this. And there's a question in general. So for images, you know that you have images, okay? You have different compression algorithms, yes, but at the end of the day, you have a matrix of pixels. That's it. That's what an image is. Everyone agrees. In the context of shapes, that's not as true. So one representation could be voxels. This is a 3D generalization of pixels. Okay, so instead of having a 2D matrix of pixels, you have a 3D matrix of pixels, and it works. You can use CNNs on it instead of 2D CNNs, 3D CNNs. Okay, it works, but it has a problem that already CNNs can be quite heavy in 2D. In 3D, it's just intractable most of the times. The resolution is like usually limited to this, maybe 128 to the power of 3, if you really have a big computer. But it's really hard to work with voxels. They're very, very heavy, and they don't get as detailed as you might want because, again, you're very limited in resolution. Another representation could be point clouds. Point clouds is just points in space. They have no order, no connection information, nothing, just points. They're cool because you can work with them. There's PointNet, PointNet++. There's a bunch of networks that work on them. You can obtain this information fairly easily with depth scanners, lidars, stuff like that. Fairly easy to get, yes. But since there's no connectivity information, do they really represent a shape? It's kind of the question. Like, they represent points in space. We see a shape if the points are enough for our eye to kind of infer the shape, but they don't really represent a shape. So can we do something better? There's meshes as well. Meshes are basically point clouds, but this time you have connection information between the points. So you have edges that connect the points in forming triangles or quads or hexagons or whatever your mesh is, but forming some kind of surface. So in this case, you actually have the surface. You have connectivity information. You can process these kind of things with specific networks called graph neural networks that works on graphs. You can see a mesh as a graph, okay? So you have nodes and edges. So you can work on them. You can deform them, yes. So you can probably optimize them a little bit, but you cannot really change their topology, and they're not so easy to work with. It's not straightforward like the other methods. You cannot change topology because if you want to, let's say, optimize this bunny to, I don't know, for some loss function, you may want to start moving the vertices around, but how do you decide when to like remove an edge or connect the edge again? There's very difficult things, and there's many ways. Yeah.
Do we have voxel for like do we have inner voxels or on the outside shape?
You can have both depending on the application. There's volume representations and surface representations.
Voxels cover only the surface. What's the difference between voxels and mesh? Because they're generally the same, no?
It kind of depends, because in a voxel representation, let's say a voxel represents a surface, so it's 1 in that voxel when there is a surface and 0 when there isn't, but you still have a whole like big cube, dense cube with zeros and ones.
Here you have only
Here you just have point with location in space and an edge that is point index, point index. So it's very light. Depending on how many points and edges you have, can be very heavy if you want, but in general, it's quite light to work with. So yeah, there's networks that work on this. AtlasNet is an example. I will not go in details with AtlasNet, but what it does is that it takes, like, think of it as a sheet of paper, okay, represented as a mesh. So it's all points, all connected, and then it deforms it to kind of wrap an object. And then it takes another sheet of paper and wraps another part of an object, another piece of paper, another part of an object. But this paper is called the papier-mâché approach to learning. So it's literally papier-mâché. So it's literally what it does, but it's very difficult to work in these kind of things because then you don't get a fully connected mesh. Then you get some weird things going on. So it works, but it's not the best approach. So there's another approach that has started to come out recently, which is called implicit representations. So this has nothing to do with neural networks. Now, in a minute it will, but for now, no, it's just implicit representations. What do I mean? For example, we can say in space, we can define a field called occupancy field, which is 1 if a point in space is inside the object, or 0 if it's outside the object. Or we can define a sign distance field, which is a distance from any point in space to the closest surface, and define it as negative inside the object and positive outside of the object. Okay. So it's a distance field and it's signed because we want to know when we are inside and when we are outside. So these two are very similar, almost equivalent. This, of course, has a bit more information. This is just definition of an SDF, sign distance field. And the cool thing is that we can parameterize the function of SDF or occupancy as a neural network. Again, so this is where the coordinate networks come up. How do we parameterize this? For example, neural networks. It's not the only way, but it's the most popular way today. So yeah, it's cool because differently from the meshes or the other representations, there's no specific resolution limit. We can sample the field at any resolution we want. Of course, the network will have some limited capacity in what it can represent. It's not as powerful as we want with any size, but there's no theoretical resolution limit. It has a limited memory footprint. The networks like this are usually smaller than the meshes. They can be used for compression as well. You can have quite a bit of details and you can vary the topology. This is very cool and very important. But we do need a meshing algorithm. So this is implicit. At some point, we want to work with the surface itself. Like, how do we get the mesh out of this? And so before we get the mesh, let's see how we can represent the SDF. So this is an autoencoder, which you have probably seen already, I assume. So you have an input, you have an encoder part that tries to compress it to some latent code, latent representation. Then you have a decoder that decompresses it and gets the output. This is self-supervised. You create a loss between the output and the ground truth, which was used as the input. So you're self-supervising this network. And you get to compress the input in the latent code. Okay, this is an autoencoder. What we use for SDF is autodecoder. So it's similar, but it's only the decoder part. So it's only the second part of the network. Oh, damn, I inverted the direction. Sorry. It's only the second part of the network, not the first. So here you have a latent code, which is the same as this. And then you have, again, the coordinates as input. Let's say coordinates in space, because we're trying to learn an SDF in the 3D space. The output of this network will be the SDF. The code represents the shape, okay? So one single network can represent one single shape if we want to. We could just not give any code. We just take one network, make it learn one shape, that's it. Or it can represent multiple shapes. This is usually how it's used. So we get a latent code that represents the shape and the network that has learned many shapes, how to decode many shapes, depending on the code we give. And the code itself is used just like the latent queries in the perceiver resampler for Flamingo. So they are initialized randomly for each shape, and they are optimized as weights. Okay. Here, the latent code was just the output of the encoder. Here, you start randomly and you optimize for it with gradient descent. Yeah, so the latent code is flat, depends on the approach, but in the basic approaches, it's flat. This is all from DeepSDF, which is the most important paper in this field from 2019. Yeah, okay, so any question on this?
Yeah, I don't really understand how this is
This is self-supervised. Yeah, I know. I was waiting for a question. This is self-supervised. This is okay. This here we're not trying to self-supervise anything. Here the supervision is the SDF. So if we take a shape, we want to train a network to learn the sign distance field. We need to compute the ground truth and SDF. There are ways to do it. We don't have to do it by hand, but it's not self-supervised. This is supervised. They have similar names, but they accomplish different purposes. Okay, so as I said, once we have our implicit representation, we need to mesh it. So we want to extract the mesh. And here you can see like This is a 2D grid of points. Here the red is the negative distance function, the blue and the green are the positive distance function. So we kind of want to find the zero level set, okay? The zero level set of this field is the surface. And unfortunately, there is no like super nice mathematical way to just get it. So we have to use some algorithms to get it. And the most popular one is marching cubes. Very briefly how it works. I will not go into details, but here you have an example of a grid in like on the plane. So this is marching squares, not cubes. So let's say we have positive values here, negative values here, and then positive values again here. So we kind of see by eye that the surface needs to go kind of like this, okay? We need to go between the minus and the plus. It will be in the middle. So what marching cubes does is that it takes the edges that have a sign flip and it linearly interpolates the grid values and gets the points and then basically connects them, okay? This is very easy in 2D. It's quite complex in 3D, but some guy in the 80s implemented it, so nobody touches it. It works. Cool. It's a big lookup table. But yeah. So this is marching cubes. And of course, the quality of the mesh that we get out of this depends on the sampling resolution of the grid. The denser the grid, the better. Yeah. Then another method is dual contouring, which is, I mean, I don't think I need to explain it, but it's a dual method. Marching cubes is a primal method. So you sample points on the grid, and then you get the vertices of the mesh, which are on the edges. Here it's dual in the sense that the vertices of the mesh will be inside the squares, not on the edges. They cannot be on the edges in this formulation. And it's a different method, but to accomplish a similar thing, it's a bit slower. So people usually use marching cubes, but it's also a bit more precise. So it depends what you want to do. So this is the cubes version, which of course gets much more complicated in space, but not important for today. So yeah, here's a like a recap slide for the implicit representation. We have voxels, something like this. We have point clouds, which again, if they are dense enough, we can kind of see the shape. This is a mesh from AtlasNet, so a mesh that's been computed using the papier-mâché approach. So you can see probably from there all the sheets of paper kind of stitched together, which is not super nice. And then we have the implicit representation from occupancy fields. So what can we do with it? If we start from a deep SDF code and so it's a shape, then we use marching cubes to compute the mesh out of it. And then we compute some loss function out of this mesh. And then we backpropagate through the whole thing. We can optimize the mesh, or actually the surface, so the surface that comes out from the implicit field, to do something specific. In this case, we wanted to change the topology of this from this genus 0 to genus 1. We can. Okay. It's not a big deal. For implicit representation, this is very easy. There you go. And marching cubes is not really differentiable. I kind of skipped this step, but there's a way to differentiate through it anyway. Yeah. It depends what you want to optimize. So in this case, we wanted to optimize this to become, to change topology. So I think the loss defined on this has a ground truth. But in general, you don't need to. I think I have an example after. Here. So in this case, what they wanted to do, so this is not my work. This is my lab, but not my work. Wanted to do drag minimization out of this. So you have your implicit representation, you use marching cubes or whatever to get the shape. And then you want to compute the drag of the car. And then you want to minimize the drag. So you use this drag computation as a loss function. Then you differentiate through it and you try to make the car better. So you don't have a ground truth for this, but you can still optimize through it. The important thing is that everything has to be differentiable for gradient descent to work. So as I said, marching cubes is not differentiable, but there's a way to get the derivative from the shape, so it's fine. But this drag computation has to be differentiable, and that's where the hard part comes in, because the simulators for drag are not differentiable and they're very slow. So usually what you do is that you have another neural network that has learned how to compute drag out of shapes, and you use that as a proxy for drag computation. Not part of today. Yeah. Well, I mean, you can see if you want to optimize for the drag, then yes, you compute the drag. Yeah. Yeah. There is a way. Previous slide. So in this slide, we want to reconstruct shapes from silhouettes. So you have this kind of thing, which is the silhouette of the object, and you want to get the shape. So you can take a network that has learned how to represent a bunch of shapes, like many shapes, with different latent codes, of course. You start with a random latent code, random shape. You extract the mesh, you render the mesh, and you get the silhouette. Then you can apply some loss between your silhouette and the ground truth silhouette and optimize it until you get the mesh that has the silhouette that you want. This is doable. Here you were trying to optimize for a chair. Here also work from my lab, from a PhD student a few years ago, trying to get surfaces from sketches. So you literally sketch the surface, sketch some object, and then you have this neural network that you extract the mesh, and then you project it, you get the silhouette, you take the edges, and you compare it to what you sketched, and you try to optimize through it. So, I mean, these are the cases in which it works. Of course, it's not perfect. I know this work. So it's always the case in research. Okay, it's never perfect, but it's cool. It works. It's proof of concept that it can work. The problem with these approaches is that the networks, it's very hard for a single network to be very good at all the shapes, you know? So this network was trained on cars, chairs, planes, and something like that. So it was very good on those, but the rest, of course, was very hard. So there's a ton of research still to be done here, but these are possible things. Here you see the drag minimization. So we have an SUV. Everyone likes SUVs, I guess. I hate them, but want to get some less drag. Voila, you get a sports car. Who would have thought? I'll play it again. I don't know if everyone saw it. This is cool. This actually works. And this works in practice also because it's being used to set a world record for the speed on like human-powered bike. I bet you could not tell it was a bike, but it's a bike. The record has not been set by a PFL, but the guys that used that set the record used this approach to do it, which part of it is from a PFL. Also from Neural Concept, which is a spin-off of a PFL. All right, so what if we want to instead represent shapes like this, like cars or chairs or whatnot that have a volume inside? Some other shapes don't. Let's say this t-shirt. This t-shirt doesn't have any volume inside. It's open, okay? It has an edge. So it's completely open. We cannot use an SDF because there is no inside or outside. So how do we do that? And this is a problem in general, not just because of like garments, for example, that don't have an inside or an outside, but also cars. It's true that they have an inside and an outside, but in general, when we have data sets, the most used data set here is ShapeNet, which has a bunch of shapes that are cars. They're not watertight, so there is no inside or outside. You have to heavily pre-process them in order to get something that is watertight and do something with it. So can we work with open meshes somehow? And this is more of my field. So yeah, so the problem with UDF, so we can use UDF instead of SDF. It's still distance field, but there's no sign. The problem is, how do we extract the zero level out of a distance field that has no sign? We cannot use marching cubes. We cannot use the other algorithm. They all need the sign to get the sign flip. There is no sign flip here. We are not differentiable on the surface because, I mean, on the SDF, you go from minus values to zeros on the surface and then positive values. With the UDF, you go from positive to zero and then to positive again. It's like an absolute value. There's a singularity on the surface. So here we cannot differentiate on the surface. You need some networks that can learn this nicely, because on SDF, it's easy to optimize a network to do it. On UDF, it's not, because it's very difficult to have a network converge precisely to 0. They usually do this, kind of U thing where it doesn't really converge. So it's a hard field. There's a bunch of work going on here, and I'm trying to work on this too. So this is a paper from 2022 by me and some other people in the lab. So what we want to do is that we want to take a UDF and we want to get a mesh out of it. And the way we do it is that once we have a UDF out of an implicit neural network, we can differentiate from the output of the network to the input to get a gradient of the UDF. So it's the derivative from the UDF value to the x coordinate, to the x-axis, UDF y-axis, UDF z-axis, okay? So we have a spatial derivative for the UDF value. And we can interpret the spatial derivative as a gradient by normalizing it. And this gradient points away from the surface, because the UDF increases when we go away from the surface. The distance increases. So by knowing that the gradient points away from the surface, we can kind of look at this and say, okay, so this goes away from the surface, this goes away from the surface, this goes away, so there must be a surface in between, okay? So this is what we do. We compute dot products between gradients to get the positive and the negative values. Of course, these are not really positive or really negative, because there is no inside or outside. We just need the difference, like a contrast between them, to get that there is a surface in between. The way we get the surface is marching cubes. Of course, I mean, this works, but it's not so precise, because the gradients are not always as nice as you see here at all. So to make it nicer, we have a voting scheme that closes most of the holes, not all of them. And then I modified marching cubes to be, instead of actually marching cubes, to be a breadth-first exploration of the surface. So once marching cubes finds one part of the surface, then we explore the surface in a breadth-first manner. So you can see an animation here. First part didn't play. Yeah. This is how the surface gets reconstructed. And you see that some parts like this, there was a hole here. See it again, a hole here, a hole here, a hole here. So there's a bunch of heuristics that determine when the algorithm is not sure. So it leaves them for later. After the breadth first has explored everything, you can infer stuff from the neighboring regions. So then you get better consistency into your holes. So these are some results, comparing them to previous methods, but they're not particularly important. So inflation means that instead of meshing the 0 level set, you mesh an epsilon level set. So this will have a volume inside. This is not open, this is watertight. It has a volume inside. It's like meshing a double garment. I'm not meshing the garment, I'm meshing like outside of the garment by a little bit. And this is ball pivoting, which is, it works, but it's super, super slow, because you have to sample a very dense point cloud to do it. So you see that we have like similar results. So actually see it here. So these are increasing the resolution. We kind of keep the same quality. Whereas to get a good quality with inflation, you need to increase the resolution a lot, because the higher the resolution, the closer you are to the surface with the inflation. Ball pivoting already gets very good performance in general, but it's very slow, like 1 second, 1 second, 1 hour. A bit different. And then this is a work that just got accepted to ECCV 2024, so I will present it this October. So why don't we use another neural network, another one, to, instead of using this kind of heuristics and breadth-first exploration, let's use a neural network that helps us determine where there is a sign flip. So we have this neural network that takes UDF values and gradients as input, and it outputs a sign configuration that we can then mesh using marching cubes or any other normal SDF algorithm. And this is the results. So you see, mesh UDF is my previous work. This is our neural implementation with marching cubes. And this is dual mesh UDF, which is a dual contouring for UDFs. And this is our method with the dual contouring for UDFs. And the mesh quality on these bottom row is lower than on the top row because of how this algorithm works. But in general, it recovers more detail. So based on what you do, you can prefer one or the other row. But the cool thing is, as you can see, Mesh UDF, since it follows the surface, it works very well on garments. I designed it for garments, but it doesn't work as well on cars because you hallucinate triangles when they're not there. So you get all of these messy things, which you don't get with our method. Whereas dual mesh UDF is quite good, but it can produce holes. Like here, the tire is empty. Here as well, you get a bunch of holes around here. Whereas our method like finds all these holes and closes them. Okay, there's an animation. Okay. Any questions? I have 2 slides on image compression. I'm almost done. Don't worry. Okay. Image compression. So this is a cool thing. Why don't we use these coordinate networks to compress images? And the thing is, we can do it. So we can have one network that takes the XY coordinate in the image and outputs an RGB value. It's quite simple. And then instead of saving the image, we use the image just to train the network. Once we've trained the network, we can discard the image. We just save the weights of the network. Can we make the network smaller than the image? The answer is yes, we can. So this is not my work, but I'm trying to work on it too. I have a couple of projects on this. This is called Coin. It's a paper from a couple of years ago, 2 years ago. Yeah, 2021. And these are their results. So they try to do this exactly as I said. The bit rate is the bits used per pixel for like saving it. And the PSNR is a measure of the quality of the image. So you see that, of course, the more bits per pixel you use, the higher the quality. And it's cool to see that this purple line is JPEG. So for very compressed images, this neural approach is better than JPEG. Then at some point, JPEG is better. Okay. These other methods are other neural approaches. So, okay, no, this is JPEG 2000, a better version of JPEG, using wavelet instead of Fourier transforms. But these other are neural approaches that are better than this compression approach. But this was the first work, so it didn't matter if it was not the best. The other neural approaches are autoencoders. But the bad thing about autoencoders is that you need a big data set to train them. And then will they work on any image? In this case, you have one network, one image. No need to do anything else. You can train them in a few seconds on a smartphone. A few seconds is still too much for a smartphone to save an image, but maybe eventually it will get there. And this is another paper that came right after 2022, in which they do something more sensible for this compression pipeline. So they have a meta-learned initialization. Let's not go on it. But they take a network, they overfit it, then they quantize it. Quantize it means that usually weights are like 32-bit per weight. Quantization means that they use only 8 bits. Okay, they go in 8 floating point precision. They quantize it, then they re-optimize the network to be a little bit better on 8-bit because the first overfitting was on 32-bit. So if you just quantize it, it's bad. So you kind of retrain it. Then you do some entropy encoding, which is lossless compression of the weights. Then you take the output. Is this better? Yes. So here you see, so this is JPEG again. Then you have this purple, which is the previous approach. And then you have the blue, which is the approach of this paper. And as you can see, it's basically always better than JPEG. And some results here. See, ground truth image, JPEG, JPEG 2000, and this neural network. I don't know if you see anything, but you will have the PDF of the slides. So you see that the JPEG is just terrible in this case because this is very compressed. So they're trying to compress the image by a lot. JPEG is good in general, but if you compress it too much, you know it's crap. So this is crap, whereas this is totally usable. It's not the best image ever, but it's usable. It's very compressed and usable. 0.08 bits per pixel is very, very small. Same goes for the bottom row. That's it. I'm done.